All right. Well, welcome or not welcome back, guys, as in me. Today is a new series alert. It's called Doing My Homework Until I'm Done with School every day. Basically, I have like what I've noticed is that my other series that I started 8 days ago called Programming Every Day Until I Finish 100 Textbooks has allowed me to actually be something I haven't been most of my life, which is consistent to some capacity. I'm not saying I'm perfect, definitely not. I mean, we're still on chapter 2 to 3 of that, but two of that, but it's good. You know what I mean? So yeah, I realized that getting a little too consistent at that, but not consistent at my homework, which is like kind of integral. And speaking of integral, let's start talking about integrals because we're welcome to calculus 2. Yeah, okay. Anyways, let's go have some fun now. So let's get started. So what we're learning here is about, in this specific situation, we are learning about, this is from memory, right hand, left hand, and I believe left, right, and midpoint approximation under a curve using rectangles. I think this uses part of Riemann sums or something like that, but this is like left-handed, right-handed, and midpoint. So I did this first problem, or I did this in the library. Well, let's continue. So let's say the graph of the velocity of a braking car is shown. Use this graph and a midpoint sum with 6 equal subintervals to estimate the distance traveled in feet by the car while the brakes are applied. So let's get started, shall we? Okay. Here I'm literally pulling out my notebook from class. It says reading notebook on here because this composition notebook is literally from 10 years ago. I literally was like, man, I need a notebook. I looked over. Oh, there we go. I had this and it had like literal drawings in here and I had to like rip them out from when I was 11 years old. I am no longer 11. You can see some remnants of it. Look at that. I have like a random face looking there. It's kind of cool. I'm drawing it. Look at that eyebrow. How high defined eyebrow. We also have a nice trip. I was doing some crazy graphic design here. Look, that trip right there. That don't tell me like Apple Music don't do that one for the Super Bowl. Like they did that like that stretchy logo look for 2025 Super Bowl. Anyways, let's continue. This is homework 1. We have 3 homeworks to do with integrals. And we have to do our coding as well. So let's hop, skip, and a jump on it. So let's see. We're reviewing a couple of things. We have rate of change. We have function of rate of change slash derivative. We have axn equals, so that's basic derivative. It's just the power rule. No, so a derivative and an antiderivative, and then no, we have a basic derivative that's anx n minus 1. So basic derivative f of g prime equals, so f of prime g plus f of plus g prime product rule. Basic things. X squared plus 1 sine x plus 1. F of x 2x sine x plus 1 plus x squared plus 1 cosine x. Yeah, we're doing a product rule there. Quotient rule. Composition. The inner. So yeah, f of g of x, g times x, f of g of x, f of g of x, I don't know, f prime g of x, g prime of x. Yeah. Okay. F of x equals sine x squared plus 1, sine of x as it goes from, Yeah. So sine of x squared plus 1 would be cosine, since we're getting the derivative of the outer term, and x squared plus 1 times the derivative of the inside. So that's basically chain rule, x squared plus 1 prime. We have our derivatives, logs, our exponentials, it's true. And then we just have some basic trigonometric, I believe, derivatives right here. So we have, or is it derivatives? Yeah, they're derivatives, yeah. I was like making sure they're not antiderivatives. We have sine of x equals cosine x, cosine x goes to negative sine x, tan of x goes to secant x squared. We have secant of x goes to secant x tan x. Cotangent of x goes to minus cosecant squared. Cosecant x goes to negative cosecant x cotangent. Yeah, they're kind of inversely related, so you'll have it. Notice that I was getting confused before, but now that I look at it, tangent of x. That's neat. So basically, when you multiply these, interesting situation. Cosecant x squared is the same. So it's like the opposites. They're all just opposites of each other. Me when I'm opposite like that, hashtag opposite day, like that, you know what I mean? So yeah, secant x squared equals secant x equals secant x tangent x. Cotangent x equals negative cosecant x squared. So cosecant x equals negative cosecant x cotangent x. Then we have composition, so, or chain rule, I believe. It's so you have e of g of x goes to e of g of x times g prime of x. So in the law, the inverse of g of x, ln of g of x equals 1 over g of x, because we again are multiplying. So like the derivative of ln is 1x, 1 over x, I believe, and then we're multiplying it by the derivative of g of x, but in this case we'd have g of x in the product. I don't know, it doesn't have the derivative sign, I gotta look at that. Ln g of x. I thought it was a chain rule, so you'd have to multiply by the derivative of g of x. I don't know. Derivative equals predicting the slope of a tangent line locally. So on a specific graph, we're trying to understand the behavior of a derivative of the slope locally. So if we have a curve of x, f of x, a, f of a. So we have a, and then we have f of a. Yeah. F of a, f prime. The rate of change in which the curve is changing, so crazy, is this guy that my professor is given as an example, because they're locally the behavior is accelerating very quickly, so the curve is very steep. And then we have a guy who's not crazy. He's like a parent driving whatnot. You know what I mean? Has kids in the back. So it's gradually increasing their speed. But they're both increasing. Like the derivative of f prime of a is still greater than 0, so it's still positive in the derivative when we differentiate. So, good to know. Alright, next up, the rate of change will be given. So the rate of change in this case, when we were going to classes, we were told to change our mentality that f, lowercase f in this case, is going to be our rate of change, and I believe f capitalized is going to be our exact area or something like that. It's the antiderivative or the integral. So then we have f of x, f prime of x equals cosine x plus x squared. P of t goes to v of t equals p prime t. P of t, v of t goes to pt. Ah, okay. So velocity will be given p of t as v of t goes to p of t nx n minus 1. So let's see. sine of x plus x3 over 3, 2. So v of t goes to p of t. Alright, my B gang, I'm back. My mom made dumplings. Or sorry, yeah, she did. This is like a fried wonton type of dumpling. Very impressive. And she made steamed ones as well. That tastes legit. That legit tastes like from a Chinese restaurant. That is crazy. That tastes legit. It tastes more legit than some Chinese restaurant, bro. That tastes. I'm like, bro, tastes like shrimp a little bit too. Hmm. Yeah, I think she made them out of shrimp. Bruh. Let me not forget all of my thoughts. Insane quality. That was so good. Wow. So let's continue forward. It's very hard to see, but So sine of x plus x3 over 3, 2. So we have cosine of x going of x plus x squared going to sine of x plus x cubed over 3. Because we add 1 to the exponent and we divide by the new exponent. Because that's the opposite of what we do in the power rule. And so to set all the functions whose derivative is cosine x plus x squared, we have sine x, yeah, plus x cubed plus over 3 plus c. And c is any number because we genuinely don't know. We can't, like, the anti-derived from a derivative, the constant, it kind of gets lost because it's like thrown in a meat grinder. You just kind of don't know. You can kind of assume it though. Elongated s is one we use when we're doing an antiderivative. So d over d of x is differentiating in respect to x. So cosine of x plus x squared is sine x plus x cubed over 3 plus c. So maybe some constant. And this is the machine we have. So we have f of x. So d over d of x. So d in the derivative in respect to x. That's going to be when we derive, always. Cosine x plus x squared. And when we put it through the meat grinder, that is the capital f of x, which is our antiderivative, we are integrating. Think of it like you're doing an opposite meat grinder moment, where you're putting our negative f of x through it, and we're getting elongated symbol d of x, and we get capital F of x, which is our antiderivative, but we're integrating. And it's like, change your mentality, you know what I mean? We're integrating. You know what I mean? But yeah, so then v of t equals 2/3 t squared minus t. P of 0 equals 2. So 2 miles away from origin. So what does P of t equal? So P of t goes to V of t. V equals D in respect to D of t. As I believe we're differentiating here in respect to t. So P of t, or P of t, V of t. I don't know. Taking the antiderivative of D of t. When we do P of t? P of change? I don't know. Don't put one in my head. No. So elongated s 2/3 t squared minus t dt. So 2/3 f of t squared d of t squared dt minus f of t dt. P of 0 equals 2. P of t equals 2/3 t cubed over 3 minus t squared over 2 plus c. Really needed to work more on antiderivatives. Our high Q was just, for that in Calc 1, that was not it. P of O equals O minus 0 plus C equals 2. P of T equals 2 over 3 T third T cubed over 3 minus T squared minus 2 plus 2. Differentiation, integration, antiderivative AXN dx equals A. Xn plus 1 over n plus 1 plus c. So, well, I think we're just learning about general antiderivatives here. So, v of t equals 2/3 t squared minus t. P of O equals 2. So, P of t is what? And so, if we understand our entire situation here, 2 miles away from origin, so v equals d over d of t. pt pt P of t, V of t goes to P of t. Eh. So when V of t goes to P of t, it's the antiderivative of D of t. For the original function. Okay. So then, antiderivative 2/3 t squared minus t d of t. It's 2/3 f 2/3 f t squared dt minus ft dt. P of t equals 2/3 t cubed over 3 minus t squared over 2 plus c. So P of 0 equals 2. So 2/3 f of t squared d of t minus ft d of t 2/3 t cubed over 3 minus t squared over 2 plus c. So 2/3 ft cubed squared d of t minus ft dt. Squared. So 2/3 t cubed over 3 minus 2t squared over 2 plus c. Okay. Minus t squared. Antiderivative, we know. I gotta really study this part because I'm gonna look confused here. So elongated s 2/3 t squared minus t d of t dt 2/3 ft squared d of t minus ft dt. So t squared minus ft dt. So 2/3 t cubed over 3 minus t squared over 2. T squared over 2 plus c. Okay. P of 0 equals 0 minus 0 plus c equals 2 because that's our y, that's our, okay, that's our f of x at 0. So P of t equals 2/3 times t cubed over 3 minus t squared over 2 plus 2. Minus t squared over 2 plus 2. What I'm trying to understand here is why did we do that? So we have 2/3 f t squared dt. Okay, so we anti-derived here. Minus, okay, t squared over 2. Okay, because we added 1 to the t plus 1. 1 plus 1 is 2. T squared 2 over t squared over 2 plus some constant plus c. So we have p of t equals 2/3 t cubed over 3 minus t squared over 2 plus c. And so we have 2, if we go back one line, we get 2/3 f of t squared minus dt minus ft dt. So I don't know why we did ft dt. I don't know why exactly. ft dt. So we haven't differentiating in terms of that. Was that supposed to be an elongated s by chance? Or what exactly is happening here? ft dt. 2/3 ft squared dt minus ft dt. We gotta search that one up a little bit, but what I understand from this is that p of t equals 2/3 t cubed over 3 minus t squared over 2 plus c, because we are we are integrating from the 2/3 f of t squared d of t minus ft dt because we had an original antiderivative symbol of elongated s for 2/3 t squared minus t dt. Okay. Alright. So sigma, oh sorry, that's not, it says sigma. What does that mean? So let's see. What does elongated S mean in calc? The elongated S symbol refers to the integral symbol, yes, used in calculus, which represents the operation of integration. This symbol was introduced by mathematician Gottfried Wilhelm Leibniz and is derived by the Latin word summa, meaning sum, as it signifies the summation of infinitely small quantities. Okay. Infinitely small quantities. Little, lot of little money, sorry. Okay. Sorry about that. Anyways. So then we have integration of 2x cubed dx equal, and so we're integrating 2/3 cubed in relation to x. So that equals 2x x to the 4th power over 4 because we're integrating 2x cubed, and then we do plus some constant. Awesome. So that equals 1 if we simplify it, right? If we take our 2 and we take our 2 and we move it over, we have 2x to the 4th power divided over 8. And so 2x, I guess they simplify to 1/2 x quad 4 plus c because we're 2 over 4, and I guess the x4 is its own base, an exponent, so 1/2 x4 plus c. And then sigma a of x minus 1 d of x equals a x negative 1 plus 1. So when we integrate a of x negative 1 to d of x, we're adding 1 to the exponent's place over 1, which is the same thing. Oh no. But if we add a 1, that makes it 0. So a of x to the 0 power over 0 will just plus c. Well, that is what it is. I don't think we need to simplify that further because he didn't simplify it further. A of x 0 over 0 plus c. And then we have integrating a of 1 over x d of x. So a equals a, integration symbol 1x dx equals a ln absolute value x plus c. Because in this case, x is in the negative. I think it's, well, it should x1 1 over 1x 1 over x to the 1st power. It's still yeah. So if we're trying to integrate in terms of d of x, then a ln absolute value x plus c makes sense. So 1 over x equals ln. So now we're integrating 1 over x squared plus 1 over x d of x. So integrating those two, what we're going to do is bring up our brochachos from their exponent, because we don't like dealing with fractions. That's what I noticed. Is that what we're going to do is we're going to bring up our base of x squared and x. We're going to bring it on up. So we have our sigma, or is it summa? We're summing, right? We're summa. It was so summa. What is elongated s in calc? Remember it was summa? Integral symbol. Okay. Alright. Good. Okay. Next up. So we have about x to the negative squared plus 1 over x d of x. So, I don't know why we didn't do that for the other one, but okay. So x negative 2 plus 1 over negative 2 plus 1. And then we did ln of x. Okay, maybe because 1 of x is already ln. And we did the absolute value of x plus c. So when we do 1 over x, we have to do the absolute value of plus c when doing our final integration steps. So that equals x minus 1? Divided by, oh, because we're dividing it by our new exponent, so negative 2 plus 1, which is x minus 1 over negative 1 plus ln of x plus 1, ln of x plus c. That's 100% correct. You don't need to simplify it further, but if you're for the beauty of mathematics, you can do x minus 1 over x plus ln of x plus c. so you can have a nice, beautiful, mathematically beautiful final antiderivative or integrated statement right there. So then we do sigma a of x n d of x. So that is basically a of x n to the n plus 1 over n plus 1 plus c. So n is not equal to negative 1. So a of x n plus 1 over n plus 1 plus c. But n does not equal negative 1. ln of x plus c, n equals negative 1. Wonder what happened here. So sigma of a of x to the nth power d of x. So a of x n plus 1 over n plus 1 plus c. N is not equal to negative 1. Because if we were to put negative 1 in this situation, what we would have is that n minus negative 1 would make it that a of x would be to the 0 power, and n plus 1 would be 0. So you don't want to have a 0 over 0 type plus c. So then basically I think it's trying to evaluate our derivative or our I think it does. It's evaluating our integral at how it will not be negative 1. So ln of x plus c comma n does equal negative 1, but that's only for the part where ln of x is involved for some reason. And so x is to the n power, but if we do n negative n, I don't know. Why exactly would that be? I'd reload plus 1 negative x to the first power plus x plus n plus 1 over x n plus 1 ln of x plus c n minus 1. Alright, sigma x e to the x blessed dx equals this. So basically some formulas to just know is that the sigma for the integration of e of x and d of x equals e to the x plus c. So when we're integrating e to the x derivative, we're just getting e to the x. So e to the x is always itself plus c. Sine of d to x, that's the derivative of sine x d to the derivative of x is cosine x plus c. And then we have secant x squared d of n derivative of d of x. That's going to be tangent x plus c. I wonder for secant x squared, actually. Secant x squared. I guess it's gonna go back to tangent x plus c. Okay, good. Happy. Okay, we're learning antiderivatives by first principles. I'm actually just reviewing my notes. Oh no, do I have to charge this? And did 30 minutes pass where I was explaining you my notes? Good thing. Alright, let's see. One moment, let me put this on charge. Alright, we're back. Took a break for a minute now, did we? Okay, so it's now 10:16 p.m. I love that for me. No, I don't. Okay, anyways, it's alright. So just looking back at this, we have the sigma secant x tangent x d and derived relative to x equals secant x plus c, because we have secant x when it's integrated into when we have secant x tangent x derived, or the derivative in relation to x, it gets integrated back into secant x plus c or some constant. Again, the meat grinder philosophy, if you look back here in our thing, is that when we're integrating, our f of x goes up the meat grinder, and it's like we're trying to repiece it back together, but we lose the integrity of it. So f of x, which the capital F of x is our antiderivative, or our, so that is basically gonna be secant x da, 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 da. Let's see. Secant x squared d of x equals cotangent x plus c. So, no, where basically secant x tangent x dx is going to be, yeah, it's going to go back to being secant x plus c. And so then we have cosecant squared d of x. So cosecant squared is going to be cotangent x. Oh, wait a minute. Hold up, wait a minute. It's the postman. Cosecant x. Oh, yeah. Cosecant squared x. Cosecant. Well, shouldn't that be negative cosecant x squared? Well, there's a minus up front. Yeah, look, it's written right there. So, minus cosecant x squared is going to be... I should really get on those projector things. That would make it even usefuler when I look back at this. So, minus cosecant x squared d of derivative, or d of x. What does d of x really mean? Let's search that up, too. What does d of x mean in calculus? Just so we really know. D of x represents an infinitesimal change in the variable x calculus. It describes derivatives and integrals and reduces with very small change, helping to express rates of change under the curve. What does dx really mean? Calculus terms explained. So, the symbol dx comes up everywhere in calculus. For example, y is a function of x, but sometimes we write the derivative of y with respect to x as in the following. So the derivative of y in respect to x. Because x is going this way, we know that. But the derivative of y depends of x is in relation to x. So where y is where x is. Ooh, interesting situation. Interesting situation. So when we write definite integrals, they're written as f of x, d of x. When we with d, f of x with respect to x. When we write integrals, they're written as summa. What is this? What is this? Long s in long s in calculus. So so the archaic variable, the symbol s, the integral symbol. Yes, the integral symbol. Yes, okay. Ash. Love Wikipedia. Ooh, latex. Ooh, Unicode. Latex. Ooh, bro, high key, Wikipedia is so far. Like, you kind of forget how far it is. High key, you can learn about anything from Wikipedia, right? Like, I'm getting distracted now. Whoa. Ooh. Ooh. What is this in a Python? Explicit is better than implicit. Simple is better than complex. Readability counts. Special cases that are unexpected. Practicality beats purity. Should never pass silently unless explicitly sounds. Probably one obvious way to do it. Okay, fine. The latex probably works of what? 1984? Wow, 2 years ago. Okay, anyways, we have some. This is going to be the integral symbol. See below, not to be confused with long s, esh, or voiceless pasta lower fricative consonantal sound used in many spoken languages. It is familiar to English speakers as the sh sound in ship. Very interesting. Okay, so when we write definite integrals, integral a b f of x respect of x. What does dx really mean? It's more than a notation. In this post, we'll explain the meaning of dx, try to get a better understanding of some symbols that we often see in calculus. Calculus is a study of infinitesimal change. Calculus is the study of continuous change or infinitesimal change. To get an idea of what this means, let's consider the following. Suppose you're running a race. You're beginning at the time x equals 0 seconds, and then you track your displacement as a function f of x. Your displacement function f of x. So it's about continuous change, infinitesimal change. To get an idea what this means, let's consider the following. Suppose that you're running a race. You begin at the time x equals 0 seconds, and then you track your displacement as a function. So you track your displacement, right? And so function of f of x. So the displacement function f of x is then a continuous function that varies over time. Suppose now you wanted to know your speed at time x equals 10 seconds. So x equals 10 seconds. That is a calculus question since you were looking for a rate of change at a particular time. So x equals 10 seconds. Your rate of change at one particular time. How could you do this? Well, you might estimate your speed at t equals 10 as our average speeds between time x equals 10 and x equals 11. So f of 11 minus f of 10, 11 minus 10. Yeah, this is a slope, right? Yeah, y2 minus y1 over x minus x1. So our rate of speed in time x is 10 seconds. But you can get a better estimate by choosing a smaller time interval, say from 10 to 10.1 instead, or even better, x10 to 10.01. Really, what you want to do is take the limit as the size of your time interval goes to 0. That is, you want to take an infinitesimally small change in x, then by the definition of a derivative, your speed at x10 seconds is f of 10 equals the limit as h of 0 goes to f10 plus h minus 10 over h. So the limit as h approaches 0, f of 10 plus h minus f of 10, 10 plus h minus 10. So this is our f and our y. And the reason why we're doing this is because we want to, that cancels out now, f of 10, negative 10. We should think of h going to 0 and as smaller and smaller increase in x when we take the average speed of 10x to time, 10x equals 10 plus h. Where does h get involved? Okay. Alright. So, oof. Ooh. Okay, we gotta read the rest of this because hierarchy, it's kind of getting relevant for my thing. So that is the derivative of f of x is the quotient of an infinitesimal change in y over an infinitesimal change in x. Put more precisely, it is exactly the limit of change in y over the change in x and smaller changes in x. The d of x and dy notation just captures this limit procedure and expresses it as an infinitesimal change in x and y instead. So basically, d of x as seen as in integrals. Another place in where d of x is seen is in integrals. Let's focus on definite integrals. What does d of x mean in a definite integral? So d of x here is still an infinitesimal change in x. So to see why it's there, we should think of the integral as a signed area and as a limit of Riemann sums. So as a signed area, I'm gonna do it. Okay. So the integral is a signed area and the limit of Riemann sums. Okay. So we call that compute a left Riemann sum f of x from x equals a to x equals b with n intervals. Let's compute the following to be true. The delta x equals b minus a over n. Then we take what is that? I forget what this is called. So what is this called? You know, you always think of these type of things. Let's say, what's this symbol called if we can? No, I did forget this one. Is it the Greek symbol for thumb? sigma. Wait, that's sigma. Yeah, I just want to make sure it's sigma. So sigma f of x times delta x. F of x is the change in x. When we take x values, a, delta x, a, 2 delta x, a, n minus 1, delta x equals b, delta x. What? X, a, delta x, a, 2 delta x, a, n minus 1, delta x equals b minus delta x. Okay. Water collects in my lungs. Sorry. Then as we let n go to infinity, delta x gets smaller and smaller, and the Riemann sum converges in value to the integral, which is the signed area under the curve f of x between x equals a and x equals b. A picture below from Wikipedia article on Riemann sum shows this convergence process. Let's see. So when we take the values a plus delta x, a plus 2 delta x, a plus n minus 1, delta x equals b minus delta x. Okay. A plus delta x plus a plus 2 delta x, a plus n minus 1 delta x equals b minus delta x. Okay. Stretch my bones. Alright, let's go. So, the Wikipedia article on Riemann sums shows this convergence process. So basically, we have this curve, okay, right here, and it's coming in from the left, I think, because we're starting off on the right. We're going left. Starting off on the right, we're going left. And Ray, is that right-handed or left-handed? Yeah, that's the left-handed Riemann sums. So we're coming in from the left of the curve. This is interesting, though. Did it? Yeah. And then we go from there to, because if you're going from the right, we're going from the right, we'd come in from the right, wouldn't we? Wouldn't we? La, 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 la. Well, technically, we're going to start at the left end point, but it doesn't start at the right end point. Are you sure this is left hand? Okay, continuing. Left hand. Sorry. Okay. Yeah. There we go. No, because that makes absolutely very little sense. It doesn't seem very consistent. That was like a midpoint sum, that red one, because it's like coming in the middle of it. I'm not so. And then you add the n number of that from it. Okay. We increase the n number of rectangles. Okay, continuing. Now we can see where the notation for the integral comes from. The integral sign is a continuous version of the sum sign, sigma. The bounds of integration from a to b are like the first and last x values for the summation, and the d of x is an infinitesimal.
Infinitesimal.
Infinitesimal. So basically, okay. And the d of x is the infinitesimal version of the delta x. where what we get is we get smaller and smaller step sizes in x. Okay, good. Another way to think about this is that in our integral we are summing up infinitesimally small thin rectangles with a height f of x and a width d of x to compute our sine area precisely. Hopefully the d of x is a little less mysterious now. Okay, bro, we got a little confusing in cardinal lie, but it's okay. So a d of x as seen in integrals. Another place where d of x is often seen in integrals. Let's focus on definite integrals. What does d of x mean in a definite integral? D of x here still has an infinitesimal change in x. To see why it's there, we should think of the integral as a sine area as the limit of Riemann sums. We recall that to compute a left Riemann sum of the f of x from a to xb in n intervals, we let the following be true. Delta of x equals b minus a over n. True. Then we take the definite integral by taking the sum of f of x times the change in x. Yeah, because we're taking little sums of all the changes in x. Like, look at it. Yes. And where x takes the values a plus delta x, a plus 2 delta x, a plus n minus 1 equals b minus delta x. So a plus delta x, a plus 2 delta x, a plus n minus 1 delta x equals b minus delta x. Okay. A plus delta x, a plus 2 delta x, a plus n minus 1 delta x. N minus 1 delta x equals b minus delta x. Alright, this is where the d of x comes in. D of x is an infinitesimal change in x. We can think of d of x read as dx. Oh, we can think of dx as an infinitesimally small change in x. The d in dx should remind you of delta. Okay. Which is a symbol for change. The dx has no numerical value. Rather, it captures this idea that occurs a lot in calculus of taking the limit of smaller and smaller intervals and smaller interval sizes to figure out something precisely about a continuous function. We can see this if we revisit our speed example from earlier. When computing our derivative, f prime of 10 equals limit of h of 0 goes to f of 10 plus h minus f of 10, 10 plus h minus 10. The bottom of this fraction is 10 plus h minus 10 as h goes to 0, which is an infinitesimally small change in x. We might therefore think of a denominator as h goes to 0 as d of x. Let's see, the bottom of this fraction is 10 plus h minus 10 as h goes to 0, which is an infinitesimally small change in x. We may therefore think of the denominator as h goes to 0 as d of x. If we let y equals f of x, then the numerator of this fraction is f 10 plus h minus 10 as h goes to 0. Okay. Why do we have the h going to 0 as we take smaller and smaller increases? A definite integral. So the derivative of an integral can be used using the fundamental theorem of calculus, which states that f of x equals f b a x f of t dt. Then the derivative capital F prime of x gives you the original function evaluated at the upper limit. Yes, so true. So Leibniz integral rule. In calculus, the Leibniz rule for differentiation under the integral sign, named after Gottfried Leibniz, states for an integral of the form integer a b where f of dt, where in t, the derivative of this integral is expressible as constants rather than functions of x. We have a special case of Leibniz's integral. Let's try and come back to that. Okay. D of x. Wow. Would love some water right now, man. Man, get up and do that. No, man. Alright, let's see. Let's go back. I'm logged out. Let's open WebAssembly, please. Okay, I'll be back, guys. Give me a second. Bro. I also realized that I literally never stopped showing my screen. I never showed my screen. That's okay though. It's for the better of the world, I suppose. So graph the velocity of a braking car is shown. Use the graph and the midpoint sum with 6 equal center sub-intervals to estimate the distance traveled in feet while the car brakes are applied. So this one needs some paper. But if it's using a midpoint sum with 6 equal intervals, we need to do a Riemann sum in this case, so delta x over n. And so basically we need to first understand the definite integral associated with this specific course of thing. But the first thing we need to figure out is actually what the original function, because the original function is given. So we actually memorize express summation, we just have to estimate. So let's just do that. So let's see what these are going up by. So let's see, we have 15, 30, 45, going up by every unit of 2. So this, I'm assuming these are going up by tens or something, maybe. So might be wrong, actually. Or maybe 5, 15. Okay, they're going, no, because it's the half of 15, 7.5. Because that might make more sense now. Because 7.5, let me think, y'all. 37.7, wait, it's 37.5 plus 7.5 is going to be 34, 44 plus 1, 44 plus 1, 45. Yeah, I think it might be 7.5 in this case. Alright, 7.5. Alright, let's think a bit more. So if this unit, I wonder if I could draw on, okay, thank you for being that way, I appreciate it. But I just like use the, I remember you can use the snipping tool, because that's what my meteorology professor does. Let's see. So let's take this function right here. Let's try to attempt it ourselves before we get all in there. So let's see what's wrong with you. Let's go with black. Yeah. Microsoft, what's happening here? Okay. Maybe I just try. I don't know. Okay, Microsoft, come on. Should I get my mouse? I can't even get a piece of paper. You want to get a mouse tool? A mouse cookie? I have a drawing tablet. 15 plus 7, 22.5. Yes, it's 22.5. What if we... 22 plus 7 is 29. That's 1 is 30. So 22.5. Okay. 22.5 plus 30 plus 7.5 is going to be 37.5. a little bit better with the sensitivity. Alright, so now we need to just label our midpoints. Or, well, actually, we need to first label all our units. I don't know why they did that to confuse us, but no. 4, 5, 6. So then, let's go make our midpoints. Go, shawty. It's your birthday. Go party like it's your birthday. Who said that? 0.5. We have 1. Then we're going to do 1.5. And then we're going to do, let's actually, I think I'm going to erase the conniving original points. Maybe they did that for a purpose. I mean, sometimes we think we know what we want, but maybe it's just maybe more confusing that way. So let's say 0.5, 1 case, 1, 1.5, 2, and then we're going to have 2.5. That's why did I get a random twang, a random accent? I don't know. 3.5, going to Six Flags, which is fun right now. Never been to Six Flags. I've been when I was a kid. I don't know. What? 4.5, twang, and then and then get another 0.5 and 5, and then get 5.5. You know what I'm saying? Boom. Wonderful. Alrighty then, what we're gonna do is we're gonna take this ain't gonna take this number. Okay, we're gonna take our some boxes. Oh, this is gonna make it more convenient. Yes, ma'am. Okay, so we gotta start off first with our first box. So f of x is it's gonna be right here. Boom, 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 boom. Okay. It was like, it's a little under 45 because I'm going, okay. 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 Might be even smaller actually. Alright. Wonderful. So let's try to guesstimate these values, I suppose. So if this is 37.5, and this is roughly halfway between those two, 45 instead of 37.5. You'd think I did a calculator at this point, but that needed my point, guys. So if we know every one of these is going up by 7.5, then I guess what we have to do is divide 7.5 divided by 2. So 7 divided by 2 is going to be 4.5. And then 4.5, then you have 0.5 divided by 2, so you have 4.5 plus 0.25. So 4.5 plus 0.25 is going to be 4.75. So 4.75. So 4.75. So 4.75. So if this is 37.5, 37.5 plus 4.75. I don't know why I'm talking like that. I'm so sorry. 4 plus 7. Okay. Maybe I need to get a calculator. Maybe I need to get a mind. Oh wait, I can get another calculator tab. This makes life easier. Oh yes, okay. So let's do 37.5. That's not what I actually did not mean to type that at all. That is ridiculous. I don't even know how my fingers did that. 37, because 37. I was trying to go 37 and I clicked 67, sorry. 3.75 plus 4.75. equals 42.25. So we're gonna name you 42.25. Okay, moving forward. We got 30. I'd say that's dead on 30 right there. I say so. Good enough for me. And then we got 22.5. I say it's 22.5. It's good enough for me. You know what I'm saying? And then we got, I would say it's a little under 15. Could we say it's a little more than that? No, it's a little underneath it. It's not exactly halfway. It's okay though. I'd like to move forward right now. Second, see, 7.5. Okay, now. So let's see, 15. It's like a 3/4 of the way up there. So 7.5 times 3/4. What does that give us? Let's see how I did that. 5.625. So 5.625 plus 7.5 is 13.125. I don't think it's that precise, but whatever. 13.125. Okay, next up, say it's right in the half, so let's go with our original. Is it 4.25? No, 7.5 divided by 2. It's 3.75. 3.75. 3.7 and hit with a 5. 5, 5, 5, 5, 5. Rest of velocity. So then, aren't I supposed to then take this number? Isn't this supposed to be the rate of change, or I don't really know. So I thought it was supposed to be a right-handed Riemann sum. So if I take these numbers and I just I try to come on, help me out here. Come on, help me. It's not clearing. See, 42.25 plus 30 plus 22.5 plus 13.125 plus 7.5 plus 37.5 plus 152.875. 152.875. Let's watch it.
The velocity graph of a braking car is shown. Use it to estimate the distance traveled by the car while the brakes are applied. Okay, so we know that trying to estimate the area underneath a velocity graph, the graph of a velocity function, will give us the distance traveled, an approximation of the distance traveled.
Yeah.
But since our function is decreasing, we know that a left approximation will be an overestimate, and a right approximation will be an underestimate. So we're going to try using a midpoint
Oh, wait a minute.
approximation.
Aren't I supposed to subtract? Oh.
Alright, and we're going to take
x0 minus
delta
x1.
t to be 1, meaning our subintervals from 0 to 6 are marked like so. But we're using midpoint approximation, so I'm actually going to use the midpoint of each of these intervals to determine the heights of my corresponding rectangles. So there's my first rectangle. This is not part of the question exactly, but It's always good to draw these kind of pictures. Okay. Alright, so there's a picture of what is going on using midpoints. Now let's try to read from the graph the areas of each of those rectangles. Okay, so we're doing an m sub 6. We chose delta t to be 1. It's just, we're trying to get an estimation, and based on the graph, that seemed like a good choice. Okay, so for the first rectangle, we're going to have the velocity evaluated at 0.5 times 1. That's our first midpoint. Then we're going to have the velocity evaluated at 1.5 times 1. Then the velocity evaluated at 2.5 times 1. Then the velocity evaluated at 3.5 times 1. And the velocity evaluated the graph of kind of rectangle. So there's a picture of what is going on using midpoints. Now let's try to read from the graph the areas of each of those rectangles. Okay, so we're doing an m sub 6. We chose delta t to be 1. It's just, we're trying to get an estimation, and based on the graph, that seemed like a good choice. Okay, so for the first rectangle, we're going to have the velocity evaluated at 0.5 times 1. That's our first midpoint. Then we're going to have the velocity evaluated at 1.5 times 1. Then the velocity evaluated at 2.5 times 1. Then the velocity evaluated at 3.5 times 1. And the velocity evaluated at 4.5 times 1. And lastly, the velocity evaluated at 5.5 times 1. Okay, so looking at this picture and approximating, this is approximately 55 plus about 40 plus 28 plus about 18 or so plus around 10. Good approximation there, plus about 4. So we're trying to read off the heights of each of these rectangles. That one's about 10, it's about 4, just short of 20, say 18. This one, just short of halfway, so 28, and so on. And doing this calculation, we get 155 feet. Now, a reminder of why this calculates the distance traveled is the
area
equation distance equals rate or velocity.
No.
Times time. So each one of these, we're taking a velocity and assuming that it happened over a full second. A velocity, whatever this was, and assuming it happened over the full second. Okay? And we got an approximation of the total distance traveled after applying the brakes to be 155 feet.
So the graph of the velocity of a braking car is shown. Use the graph and a midpoint sum with 6 equal intervals to. Honestly, being on the ground is kind of crazy lit, because it's like, you just high key sitting on the ground, bro. Like when you're in a chair, bro, you're restless, bro. You're like, I want to lay down, bro. When you're on the ground, bro, you're able to move. Bro, we should make more ground desks. Literally just put a yoga mat, put like a room-size yoga mat below one of these tables. Just grind. Okay. Use this graph and a midpoint sum with 6 equal. No. Okay, no. So it's times 1. Why did he multiply
the velocity
by 1? Why did he decide delta t is 1?
Okay.
1.
Alright,
Okay.
so there's a picture of what is going on using midpoints.
2 minus 1 is 1. 3
now let's try to read
1. 4 minus 3
from
is
the
1.
graph the areas of each.
Okay. So velocity is 0.5 times 1.
Midpoint. Then we're going to
Are y'all just guesstimating?
approximating. This is approximately 55.
55. Me when
Plus
I make up
about
stuff.
18 or so.
40 plus 28. How do you know that's 28? And that's because it's not dead center, or?
Plus around 10. Good approximation there. Plus about 4. So we're trying to read off.
Hate when you have to approximate this hard now. So let's see, maybe I'm being a bit anal or operated, but maybe that's like 43, 30, 23. Let's like round up. Let's say that's 13 instead of 13.125. 7, let's say 8. And that's literally not 7.5, dog. No, that's 7.5. Never mind. 7.5, 3.75. Okay, so then afterwards, what was our cool answer? Say we don't do. It's 52, 53. Let's go with 153. Let's engage mind tap. Take it website. 153 feet. Midpoint. Brother, you're making me approximate. I'm trying my best out here. Okay, let's try it again. 42. Okay, let's give whole number integers. 42 plus 30 plus 22. Let's see, 23 plus 13 plus 4. So let's do 112. That's a different number. That's way different. It's right. Ah, that's crazy. It's crazy, man. It's crazy. Yeah, come on, baby, do that. Oh my goodness, Euphoria. Euphoria. Okay, we don't gotta be crazy with it. You wanna read a resource on it? Hmm. The Greeks had a method for splitting up polygons into triangles and calculating that pretty far. So this question has several parts that must be completed sequentially. If you skip a part of the question, you will not receive any points for the skip part, and you will not be able to come back for the skip part. Estimate the area under the graph of f of x equals cosine x from x equals 0 to x plus x. F of x equals cosine x from x equals 0 to x equals pi over 2 using 4 approximating rectangles and right endpoints. Sketch the graph in the rectangles and determine if your estimate is an underestimate or an overestimate. Repeat part A using left endpoints. Sketch the graph in rectangles and determine if your estimate is an underestimate or an overestimate. So the left hand side graph is always going to be an overestimate because we're going above the curve most times, especially if it's actually, sorry, we're and then like I guess and then like the right hand side is most time it's an underestimate because you're going underneath it. I don't know, like right hand side, left hand side. Mm, 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 okay. Click here to begin. So cosine x from x equals 0 to pi equals 0. Alright, rectangle areas are found by calculating height times width. The width of each rectangle equals delta x, and the height of each rectangle is given by the function value of the at the right hand side of the rectangle. So we calculate r4 equals 4, I equals 1, f of x1 delta x equals f of x1, f of x2, f of x3, f of x4 delta x. So where x1, x2, x3, and x4 represent the right-hand endpoints of force equal subintervals of 0, comma pi over 2. So x1, 2, and 3, and 4 plus subintervals of 0, comma pi over 0, or pi over 2. So 4 is 1 equals to 1. Okay, so the interval equals 1. Say we got f of x1, f of x2, f of x. Hold up, y'all. Let me go get a glass of water or something. Sorry, y'all. I just came back and I had to do a little side research. I literally am sitting on the floor and I'm like, why is my life feeling like I can change? I feel like I can sit here and do work for hours. Bro, when I'm in my chair, even though I got a nice chair, bro, I mean, I got a chair with 2 levels on it that I can swivel the bottom part, like, where I can sit down like this. Like, imagine these are my feet, and you know what I mean? Like, dude, I'm literally sitting on the floor and I watched this video about how it's crazy. Like, a few videos about how longevity is literally determined by if you can stand up, like, cross-legged, and like all these different metrics of how you're supposed to sit. And literally, I kid you not, I tried sitting like splayed like this, and my left, like, it's crazy how tight my leg is. Like, it was insanely tight. And apparently, it's because we're adapted to sit in these ways. It's just so crazy how, oh my god, oh, and it's so loose now. Bro, oh my goodness, I didn't know I could be this flexible. When did we stop sitting on the floor? Literally, we're so stupid. Like, the human race is so dumb. Like, we are literally made for the floor. Like, when did we invent chairs? Why did we invent chairs? Like, chairs are cool and all, but like, what's the purpose for being elevated off the ground besides rats and mice and whatever, like, we probably dealt with back in the day or something? Like, bro, or maybe it was cold back in the day. I don't know, but this is literally so lit, bro. Like I feel healthier. I feel like how it like reduces the curve and the pain and like the anterior, movement forward. Like I started thinking back to my life, like, bro, when did we used to sit on the floor? Bro, second grade sat on the floor, third grade sat on the floor, fourth grade sat on the floor, fifth grade sat on the floor less, sixth grade sat on the floor less. And then seventh grade, bro, problem started in seventh grade, bro. When did we stop sitting on the floor in seventh grade? I don't even think we had a rug no more. I'm sorry, I gotta do a little more research on this. Like, I need to talk to. Alright, basically, I got distracted. I ended up watching a video on wildfire forensics, and now I have a lot more thoughts. So, yeah, and for coding, it's literally 1:42 a.m., bro. I cannot disrupt my circadian rhythm. I'm just gonna have to do a double session tomorrow and do lots more homework. Time management, bro.